Okay, we're going to finish up on quiz review 6.2, 6.3. Let's look at number 7. 30% of a radioactive substance disappears in 15 years. Find the half-life of the substance. So we're actually given the equation. We're going to start with R is equal to CE to the KT this time. We're not going to have to derive this. Okay. The two variables are time and radium, or this, radioactive substance. So I'm going to let T represent time and R represent the substance. So 30% of the radioactive substance disappears in 15 years. I'm going to let R represent radioactive substance remaining. Okay, so how much remains? So again, I'm going to let C represent the initial amount of the substance, since we don't have that value. So at time 0, 0 years, we have a specific unspecified amount. And after 15 years, we know that 30% will go away. So if 30% goes away, that means 70% remains. So that's why after 15 years, we have 0.7 times C, 70% of the initial amount. So we have to be careful with the wording here. It's not 30% remains, it's 30% disappears. Okay. And then it says find the half-life of the substance. So we want to figure out how much time will pass before half of the initial amount will remain. So C will turn into 0.5 C. Okay, so half-life is how long it takes before half of the amount remains. Okay, now again, this is a problem where we have to go backwards a little bit. We have to solve for K, and then once we solve for K, then we can use that information to solve for time. Okay, the time before 0.5 C remains. Okay, so the order pair available to us, we have 15 and 0.7 C, so we can plug this value in for the amount for R. So 0.7 C is equal to CE to the 15K. So to solve for K, the C's will conveniently cancel out. We can bring the exponent down in front by introducing first logs into the problem. So natural log of 0.7 is equal to ln of e to the 15k. And bring the 15k down in front, divide both sides by 15. So we have our k value, natural log of 0.7 over 15. So we have r is equal to ce to the ln of 0.7 over 15 times t. So we are to solve for k. Now let's see if we can use the other ordered pair available to us to help us solve for time. So 0.5 C plugs in for R, and we're looking for time. Okay. Again, the convenient thing is that the C's will cancel out, so 0.5 is equal to e to the ln of 0.7 over 15 times t. We want to solve for t. We want to bring this exponent down in front, so let's again introduce natural logs into the problem. So this exponent comes down, so we get ln of 0.5 is equal to ln of 0.7 over 15 times t. To solve for t, we can multiply by 15 on both sides, divide both sides by 0.7, natural log of 0.7. So this is our specific value for t. And if we plug this in our calculator, we're going to get 29.15. So we know that it's going to take a little more than 29 years before half of the substance disappears. And we're able to figure that out because we have an intermediate order pair to help us solve for time. Okay, last problem, number 8. In a certain culture where the rate of growth of bacteria is proportional to the amount present, the number triples in 3 hours. If at the end of 12 hours there were 10 million bacteria, how many were present initially? So again, we can jump straight to our equation. Y is equal to CE to the KT. Time is the independent variable. T in bacteria in millions is the dependent. So again, this is a problem where we don't have the C value, so we're going to solve for the K value first. So at 0 hours, there's going to be initial amount of bacteria. After 3 hours, that amount is going to triple, so 3 times C. And after 12 hours, there's going to be 10 million bacteria. I'm going to let this number represent millions, okay? So 10 million. Let's see what's available to us. We can use the second order pair to plug in so that we can solve for K. So let's replace Y with 3C. Let's replace T with 3. So we get 3C is equal to CE to the 3 times K. The C's will cancel out. We're going to take the natural log of both sides to bring this exponent down in front. So ln of 3 is equal to ln of e to the 3k. 3k comes down in front, divide both sides by 3. ln of 3 over 3 is equal to k. So we have y is equal to CE to the ln of 3 over 3 times t. All right, let's use the other order pair that we have. So let's plug in 10 in for y. Sorry, actually, in this case, I use y to represent the bacteria. Okay, so 10 in for y, and then 12 in for time. I'm going to solve for c here. I'm going to cancel some things here. 12 divided by 3 is 4, so I'm going to make this e to the 4 ln of 3. Plug this into the calculator. This gives us 81. Divide both sides by 81. We get 0.123. So c is equal to 0.123. And again, this value, because I'm using 10 to represent millions, we're going to represent this as millions as well. So this represents 0.123 million. So 0.123 million is 123,000 bacteria. So that's our C value there.